Thank you very much for this warm invitation. And invitations from graduate students are the highest honor, I think. So thank you very much, Jantu, for doing this and the fantastic introduction. So today I have something for you, all of you, to sort of think about and maybe ponder in your own research. This is a story that has developed over in our lab from 2014, 2013 onwards. It's now 12 years, where we are trying to sort of do organic chemistry in water. And the main concept driving this is, of course, organic molecules are insoluble in water, typically, unless you make functionalization to make it water soluble. They're typically insoluble. So, how to sort of take these molecules in water and especially use supramolecular chemistry to take them in like sponges and do reactions with them. So that's the basic uh, motivation of this work, and I will share our recent results in while we are trying to do this. But before I do that, let me just introduce a little bit of TIFR Mumbai, where I am currently a faculty member in the chemical sciences department. I do not know how many of you have visited India and Mumbai. If you haven't, the next time you visit Mumbai, do pay an attention to this institute. It's absolutely near the shore of Arabian Sea. It's a place called Kolaba, where we have the Tata Institute of Fundamental Research. It's the mother institute of an umbrella of institutes, which was founded by the Department of Atomic Energy. It's all internally funded by the Department of Atomic Energy. And we have a fantastic view of Mumbai from our own seaside. And you're most welcome to come. And you can send an email message if you want to visit. I'll be very happy to host you. So, in TIFR, I have a research group that looks at how to engineer chemistry that drives solar energy conversion paradigm. So, one of the most critical aspects of this, and since this idea is now um, kind of widespread around the world, every department in the world, chemistry department in the world, material science department in the world, they have at least one research group trying to explore reactions that are driven by solar light. And it's a paradigm that is, of course, widespread not only in the departments across research departments of chemistry across the world, but also in biology, when photosynthesis, when we think of photosynthesis. So it's not unnatural that we are trying to mimic photosynthesis, the concept of it in some form. Now, the thing that you need to do is, if you have to rationally design materials for solar energy conversion purposes, our group believes that we need to understand structure and dynamics of excited states of these molecules. And they can be done using femtosecond lasers, simply because if we can measure the reaction rates after light absorption, which takes place in few femtoseconds, I should be able to track all the events and derive mechanistic information to sort of sort out excited state reactivities, excited state structural changes, excited state redox potentials, and develop the chemistry around it. So, with that motivation, our group over the last 15 years have been trying to look at structure of excited states using spectroscopic techniques like time resolved vibrational spectroscopy. In essence, we do a lot of time resolved Raman spectroscopy. We look at structural changes in conjugated polymers, for example. What are the coordinates that do charge transfer? And we unravel reaction coordinates. For example, in this case, there was a donor acceptor polymer, which the donor and the acceptor units were connected by a molecular thiophene unit. And we found out through Raman spectroscopy, exclusively done Raman spectroscopy on the excited state, that the rotation of this single thiophene unit that connects dictates the charge transfer timescale. Now, these rotations are in the order of hundreds of femtosecond. And so we told that the charge transfer reaction only happens in hundreds of femtoseconds once the rotation has been fulfilled. So this is one of the ways to look at the problem of reaction coordinates and structural changes in the molecular systems. We also sort of perform things which allow for direct detection of vibrational coherences on the excited state, which can be now Fourier transformed to Raman spectra. So we do direct detection and indirect detection of Raman spectra, both in time domain and frequency domain. Now, the projects that emanate from these kind of spectroscopic sort of investigation involve things which are well known in the literature, where light harvesting nowadays, especially solar light harvesting, can be done not just with the simple paradigm that one excited state can be created for absorption of one photon, but you can create multiple excited states. And this is the idea of one of the molecular paradigms of multi-exciton generation called singlet fission, where you can generate two triplet states simultaneously with absorption of one photon. Two triplet states. So two triplet excitations generated simultaneously with absorption of one photon. So this is a topic for another day. I'm not going to speak about it today, but what I'm going to talk about is our efforts to do chemistry in water. And this is the idea of photoredox catalysis in water using supramolecular nano cages. So let me come to the main motivation. So we know that if you think about doing reactions in water, the first thing that goes in your mind is how biology does it. Because biology in our body or in animals or in unicellular or multicellular organisms happens with an aqueous dominated environment. And in all these aqueous environment, we know that enzymes operate, and enzymes are essentially organic molecules or amino acids stitched together, right? And the amino acids can have very hydrophobic these polymers of amino acids, which are proteins, can have very hydrophobic cavities, which are called active sites. One famous example of a protein that is called cytochrome P450 is known for its oxidative capacity in the body, does hydrocarbon oxidations like this, absolutely insoluble molecules, but they can be oxidized selectively in one of the carbon positions from CH bond to COH, okay, using oxygen as a source of our oxidant. And this has been well described chemistry for almost 30, 40 years. And these reviews can be found out in some of these papers that I've just mentioned here. There are many more papers, but Michael T. Green and J.T. Groves are leaders in this community, and students who are interested in looking at selectivity, how enzymes like P450 bring selectivity using an active site which has metal in them, can read these papers. So what has happened is over the years, people have realized that inorganic metal complexes like these iron complexes with porphyrin ligand system can sort of activate dioxygen. Activate means make the oxygen-oxygen bond weaker and break one of these oxygen atoms from this and take it and position it in between the CH bond and make a COH moiety. Instead of a CH moiety, a COH moiety. And what people have learned over the years is metal sites in enzymes, especially in metalloenzymes, are required for bond activation events. Using this paradigm, inorganic chemists across the world have mimicked these active sites and created small inorganic complexes that can operate in organic solvents and do the similar kind of chemistry, not exactly at the level of efficiency of cytochrome P450, but good enough to sort of capture the chemistry and the catalysis. What has also been learned over the years is not just that the metal active sites and the ligands have to be mimicked for the chemistry to be executed, in lab-based designs, but also we have to think about how the enzyme covers that catalyst. Basically, how it puts a coat around the catalyst. So this is very important, and people have found out that secondary coordination effects beyond the primary ligand sphere is very important to control the energetics of intermediates and pathways, and especially when they involve proton and electron transfers. So most of these reactions are redox reactions, and redox reactions, of course, involve electron transfer events as well as, in some cases, proton transfer events. So the secondary coordination sphere of the enzyme plays a very critical role. So we asked the question in our group, can we do similar organic transformations in water, exclusively in water, using this cavity concept, where the cavity will provide the necessary hydrophobicity that the enzyme is providing for the organic molecule, and also provide interactions with the molecule and the cavity to sort of demonstrate a very biomimetic kind of a reaction, like an oxidation reaction with dioxygen. The additional challenge that we took on was, why don't we just ask the question if this can be done with light? Enzymes don't use light, but we should be, as chemists, we should be able to design new paradigms with light. So can light be used to drive enzyme like transformations in nanocavities which are soluble in water? So that's the question. So before we started in 2013 on this project, there was 5 years from that point of time, there was already a beautiful illustration of new chemistry done by Nobel laureate Professor David Macmillan from Princeton University. Dave and his group sort of published a very famous paper in 2008, and simultaneously Tae-Sik Yoon from University of Wisconsin was also publishing a paper. This was published in Science, and Tae-Sik Yoon published in JACS, that you can use a photosynthetic mimic, like an idea that photosensitizers that can absorb light, and especially metal-based photosensitizers that can absorb light, can drive organic reactions in solvents, in organic solvents, where you can excite the molecule, which is a dye, an inorganic dye, a metal complex with very large molar absorptivity in the visible. You can absorb light, you can create an excited state, and from this excited state, you can do either oxidative chemistry with electron transfer so that the dye is reduced, or you can do a reductive chemistry where the dye itself is oxidized and dumping its electron to a substrate. So either one way you can go and you can complete a cycle. Okay. And this was shown by David Macmillan's group and many others for entirety of like 5 years when we started at that point, that this can be done and organic reactions can be done with light by a paradigm called photoredox catalysis. And what was kind of at that time at a nascent stage, what was understood is you need this dye to trigger the entire catalytic cycle. And you can also couple other inorganic catalysts that do not have to be light activated, but a light activated sensitizer could make an inorganic catalyst active, and then that inorganic catalyst can do cycles on their own, okay, in dark. So this particular synthetic scheme could be amenable to many classes of catalysis. You just need a photosensitizer to do this. Now, unfortunately, what was realized over a period of time, and especially in Tae-Sik Yoon's group, that which is all captured here in this chemical review article, that some of the reactions that the photoredox catalysis do, they do not allow for only the dye to start the reaction and end the reaction. There could be chain propagation steps available in the system, because what happens is these substrates, which could be the ones that are getting oxidized or reduced, they can go away from the dye and start a chain reaction of their own. So there's no control on the reactivity. There is no dictation that only the dye is necessary for every photon absorption to drive the chemistry. So when quantum yields were computed, the quantum yields turned to be more than one, which is impossible, because you would think that for every chemical step you will require one photon, even if quantum yield is one. But unfortunately, a quantum yield of 3, 4, 10, these are the numbers that were obtained, which told us that only one photon can drive multiple reactions through chain propagation steps. So it was very clear that it's not a very controllable chemistry. There could be other pathways. So one of the things that we realized, that these are diffusion limited electron transfer reactions. And every time you do a diffusion limited electron transfer reaction, you have a chance that after the electron transfer, they bifurcate off in space. So the question was, can we create these donor acceptor interactions, which are happening for the dye and the substrate, and make them stable interfaces? Let us not let the substrate escape and go away in some other part of the solution and carry on a chain reaction. So one way to think about this would be to create stable donor acceptor interfaces. And how well to do that? Well, one can think of sort of creating these supramolecular capsules, which would lead to stable donor acceptor complexes. And we know there is a lot of work that has gone on to create these supramolecular systems from early 70s up to this point on. And this is a very nice review by Rafal Klan and co-workers, who are themselves supramolecular chemists. And they had a very nice Nature Nanotechnology paper in 2020 that sort of covers all the aspects of who are the major players in developing these supramolecular capsules. And you can see Nobel laureates Jean-Marie Len and Jean-Pierre Sauvage, who have contributed to this community in a big way by making capsules or making molecular motors, for example, right? So these are very famous examples of cages, of complexes that are stable, that can host molecules inside the system, inside their capsule, and can be used to carry out chemical reaction. One such system that, or a set of systems that we focused on, because we wanted to do chemistry in water, were the set of charged capsules that we looked at. And this is the time in 2013 when we saw this, that there are lots of capsules reported in literature from the group of Fujita and Raymond and Stoddard, that showed that these are possible to make very highly charged systems that can be solubilized in water. So we asked the question using Fujita's cages in the early days, that can we put molecules in these cages and derive a charge transfer relationship between the molecule, the cage, and the molecule. So since these molecules are highly charged, their redox potentials are tunable, because if it is positively charged, they can be highly oxidizing. If it is negatively charged, they can be highly electron donating or reducing. So this was a very clear idea in our mind, that if we chose an oxidative chemical reaction, like going from an alkane to alcohol, we should be choosing positively charged cages, because then the charge transfer interaction with the molecule will be amenable to a CT complex, that charge transfer complex. So that means a redox pair of a donor and acceptor bound together generates a CT pair. And if we have that, and there is a molecular orbital overlap and interaction, we can probably think of CT states that can be activated with light. So we ask the question, can we use host-guest charge transfer interactions to activate bonds? And this is all now covered in our accounts of chemical research paper in 2025, which anyone is free to read. So idea was that when you put the molecule inside the cage, the entire system becomes colored. And you can see very nice absorption, optical absorption from 400 to 550 nanometers. That is, that can be photo excited. And these set of states are now these newly formed charge transfer states. So we can do visible light mediated chemistry with these charge transfer states. But the big question was, what are the lifetimes of these states? Since they're so closely bound together, the donor and the acceptor pair, so even if there is a charge transfer upon photoexcitation, the electron transfer takes place, still they are bound together and the radical cation and radical anion are close by. So there is always a chance of a recombination. So typically from G.N. Lewis's time in the early 40s, 1940s, to this point on, it was known that CT states don't have a long lifetime. They're typically in the order of 10 to 25 picoseconds, and that's what we've also measured in this paper, in the PCCP paper in 2021, that these are in the order of 10 to 25 picoseconds, not more than that. So what do we do with a 10 to 25 picosecond long-lived state? We can't even do diffusion limited chemistry, which are in the order of nanoseconds. So we took help from photosynthesis. As I said, photosynthesis has a secret way of you know enlarging the lifetimes of electron transfer states. And one of the ideas in photosynthesis that is well known is a process called proton coupled electron transfer. And the idea here is that what you do is, for every electron transfer that you do ever in any kind of complex, you remove a proton from the system. And if you do that, what happens is, if you just did an electron transfer, you had a charge system, a radical cation with a positive charge. Now, if a radical cation and radical anion are simultaneously together, they can still do a back electron transfer and compensate. But if you remove the charge completely from the system by removing a proton, then it becomes a neutral radical. And neutral radicals have long-lived, time scales under these conditions. So a proton coupled electron transfer would lead to neutralization of charges, and that would weaken the Coulombic interaction between the donor and acceptor. And now you have a chance to prolong the lifetime. This is the image of my PhD supervisor, Charles Dismukes, who trained me in photosynthesis for my PhD in Princeton, as Jayanta said. And we had looked at this very extensively for my PhD problem. So I knew that this is something that we can do in these synthetic systems. We can mimic nature and use this reaction, this class of reaction of PCET, to extend lifetimes. And when my PhD students, Rahul and Ankita, looked at this problem, they actually chose cleverly a substrate which has a proton transfer channel available. So you can see an OH group and an NH group. Both are ionizable residues. So we demonstrated in this 2014 paper that you can make charge transfer states with these amine class of molecules and transfer electrons and create a radical cation on these molecules. But then the radical cation loses its positive charge by just deprotonating. And we could demonstrate that by transient absorption measurements, that they have a kinetic isotope effect of 1.3. It is pretty interesting that you can do this within a picosecond. It's one of the fastest known proton coupled electron transfer reactions that synthetically can be done. So what we demonstrated was that the alcohol can be removed by an electron. You can remove an electron from that alcohol as well as a proton to create a neutral radical. So this clearly told us that we can do oxidative chemistry to create neutral radicals inside the cage, inside the host, which is a supramolecular cavity, charged cavity, Fujita's system in this case. See, the Fujita system has a very clear mandate of having, a palladium site up here and organic ligand, which is a triazine moiety. Okay, and these are flat aromatic molecules. They can be bent in the crystal structure or in the in the geometry optimized calculations, they can be bent, but they allow for stacking. You see, these are molecules are stacking across the cavity to create a CT interaction. So you can have very nice CT interactions, and you can do this very exquisite chemistry in time scales. So when we saw this result, and when we sort of saw that it can be, that proton transfer can be done after the first electron transfer can be done in sub picosecond time scale, we said this could open up a new way of looking at chemistry, simply because what we know for all these years is when we think of designing a catalyst for a chemical reaction, a selective chemical reaction, we always think about the bond dissociation energies, thermodynamics of a CH bond that needs to be activated. We know what the bond dissociation energies are. We work out a metal system or an activating system that could exclusively target that energy scale, right? We change the oxidation state of the metal. We ensure that this is a very selective interaction. But in this case, for the our paradigm, we just think about time scales of reaction rather than bond energetics. It's all involved in the bond energetics, but it's a different way of looking at the same problem. That instead of thinking about dissociation energies, why don't we think about redox potential of the entire system and pre-organize one bond to be activated within a supramolecular system and ensure that that is fast enough after the electron transfer. So this is the idea which sort of told us that if we have to develop this idea for chemical reactions, we should understand how the solvent environment responds to such fast chemistry. So Ankita, a PhD student in our group, she did a very nice experiment where she looked at the solvation dynamics of the all the water around the cavity as the reaction is going on. And she found out that the dynamics are limited to 4 to 10 picoseconds of solvation time scale. And that told us that the solvent shell equilibrates in 10 picoseconds. So before the equilibration of the solvent shell, if you do the proton transfer reaction, we are actually making sure that we are using vibrationally excited states or hot states without dissipating energy. So this is one way to ensure that the energy efficiency of the reaction is well done. However much the photon energy is, you don't want the system to relax through solvation. But before solvation, if you pick the proton off, you can do energy efficient reactions. So this was the time scales that Ankita told us from her measurements of transient absorption and solvation dynamics, which I'm not describing here right now for shortage of time. We can go through this in the question answer session. But we clearly showed that the relevant ceiling on the time scales are 10 picosecond for this gauge. So if you can do everything before 10 picosecond, I can make use of non-equilibrium dynamics in the system, which has not equilibrated, which has not lost its energy. So that would be a fantastic way of thinking about the problem. So Ankita took this motivation and she looked at a very classical problem in organic chemistry, which is called CH bond activation. And we asked the question, can this framework work? The proton coupling to the electron transfer step. Can it work? So we took this, we looked at literature and we saw that things like toluene, which is a completely aromatic hydrocarbon, has a pKa that drops from 43 to minus 20 in the radical cation state. So it was very clear to us that a minus 20 pKa is a highly acidic system. Okay, and water can extract the proton off. So Ankita took a series of these aromatic hydrocarbons, anthracene, naphthalene, benzene, as you can see, put them inside the cage, created charge transfer states. You can clearly see there is a feature between 450 to 550. It's all colored. You can see the color in the solution. If they are independent of each other, there's no color. If you take just the cage and the molecule, there's no color. You mix them, it's a colored solution. It's a CT state. You excite these systems at the CT state, you get the radical cation. We confirm the radical cation the spectra, which we obtained in few picoseconds using spectroelectrochemistry data, which means you can also electrochemically oxidize these systems and look at their spectra. And they very well matched with what we got from a transient absorption spectra in picoseconds. And you can clearly see that the toluene radical cation looks slightly different. The anthracene radical cation has a peak at 725. The naphthalene radical cation is much more broader at peak at 700. So they're all independent systems and they decay away with a deprotonation step. So we took a deuterium isotope, that means a D2O, as a solvent, and we could clearly see that there's a kinetic isotope effect to the decay of these states, which told you that a neutral radical formed. So we confirmed the neutral radical by sort of doing chemistry, and we saw the first example of doing stoichiometric toluene oxidation without any other side product of an alcohol or an acid. We just got benzaldehyde at 60% yields. When we put this into catalytic quantities of 5 mole percent of the cage and a lot of excess of the substrate, we could get 93% conversion of a single product, which is benzaldehyde, telling us that this is the only way you can do toluene to benzaldehyde and ambient conditions with dioxygen as an oxidant with visible light at 400 nanometers. Okay. So this was published almost 6 years back, and we could demonstrate that the toluene substrate using GCMS goes down in concentration while the benzaldehyde comes up, but with a lag phase. You can see it's not instantaneous benzaldehyde rise. There is a lag phase, which told us that this is like an enzyme, operational as an enzyme, that you don't release the benzaldehyde until few benzaldehyde molecules form and then gets ejected. So we could draw up an enzyme-like catalytic cycle, and which told that you can, I'll take the question, that you can load the cages with your molecule as a CT complex, excite it in the CT state, create a radical cation and a radical anion on the cage, then take the proton off that radical cation to make a neutral radical. And that neutral radical then is long-lived up to nanoseconds inside the cage. That's one of the amazing things about the nano cage. It allows for long-lived neutral radicals to stay. And then oxygen comes in, reacts with this, and creates a benzaldehyde. This is a 4-electron, 4-proton reaction, creates a benzaldehyde, and then you can sort of go forward with the release of the benzaldehyde when there is excess of toluene. So this again gets loaded up and a catalytic cycle resumes. And you can see this is different from David Macmillan's group's redox chemistry, because David Macmillan would not keep the toluene near the catalyst. It'll diffuse away. But this, the toluene is inside a cage. We are hosting it forever. So every photon will create a catalytic cycle. So the quantum yield can only be 1. It cannot be greater than 1. Yes, question. There is a question. I think there was a raise of hand. Janto, there was actually somebody raised. I guess Daru Seto, maybe. He raised his hand.
Hello, Prof. Sorry. Yes, accidentally.
Oh, accident. Okay. Do you have a question, or it was just?
No, sorry, Prof. Okay,
that's okay. Don't worry. Don't worry. Don't worry. It happens. Okay, no problem. Thank you, Janto. So this basically told us that in water, remember, we are doing all this chemistry in water. Toluene can be converted into benzaldehyde. Toluene is water insoluble. Benzaldehyde is slightly water soluble than toluene. And that allows for benzaldehyde to get released into water, and toluene gets in again. So this is a very good way of sort of cycling the entire chemistry, that benzaldehyde has a slightly higher water solubility. And this chemistry is being done in 14 picoseconds. 10 picosecond was that solvation time scale. We are just about close to that number. We still have equilibrated solvent, but we can do the CH activation in 14 picoseconds. That's actually the fastest reported CH activation reaction. So this is a phenomenal start to the chemistry, because now we can think of um, creating these neutral radicals for different kinds of purposes. What we also understood with some computations and calculations in the system, that an electric field of 5 to 7 volt per angstrom acts on that CH bond. How did we find that? Well, we looked at the Raman spectrum of the toluene molecule in pure solvent. And it turns out that the Raman spectrum shifts when the molecule goes inside the cage, and it shifts to lower frequencies, lower vibrational frequencies. That tells you the bond is weakened. And it tells you that why that activation is taking place. The CH bond is getting weakened because of all the charges in the electric field of the cage. It's 12 positive. There are 6 palladium and there are 2 plus individual metal sites. So 6 palladium makes 12 positive charges. It's all distributed in the nano cage, and that creates an electric field, and that affects the CH bond, and the Raman spectra shifts. So this was a very clear illustration that electric field has something to do with it, apart from the light. So the bond activation is taking place in the ground state with electric fields, and then you use light to activate it further and create these charge transfer states. So we used time resolved vibrational spectroscopy to look at this problem. And we asked the question that, can we follow this CH bond activation in real time and see when exactly the bond is broken? And what are the limiting aspects of the bond breaking step? So Shunandita, who is gone for a postdoc now, looked at this problem, and she asked the question, what is the role of a water cluster around the cage that allows for this proton transfer to take place in the first place? So she looked at a system which was specifically designed, a substrate that was specifically designed. These are bithiophene units as a substrate, because thiophenes have good Raman cross section. So if I want to do excited state Raman detection, I should be able to excite and look at the Raman signatures. I should have enough Raman intensities. So we chose this thiophene substrate for that reason, because it shows good Raman spectra. But we quantified initially the transient absorption spectra that you see here. So transient absorption is a technique that looks at excited state phenomena. And you can clearly see that after photoexcitation, if I look at the system at 300 femtosecond, 600 femtosecond, 1 picosecond, 2 picosecond, and so on, the absorption spectra is evolving in time. This is the absorption spectra, the pure absorption spectra. And these absorption spectra, that at 470-75, they come from a radical cation on the dithiophene unit. It's well reported in the system, and that decays away in hundreds of picosecond. And what remains is a very small signal that you can see at the end that remains in nanosecond. So that we thought could be the radical, neutral radical of the bithiophene system, but we were not sure because it's such a small signal. We were not sure how much of the radical has been created. So we had to make sure that, can we look at that bond breaking step using time resolved spectroscopy of vibrational spectroscopy. So transient absorption told us that this transition from the radical cation to the neutral radical took place in 60 picosecond. You see the 60 picosecond time scale? And it has a kinetic isotope effect of 1.4, close to 1.4. That told us that indeed bond breaking is taking place. But when Churandita did this femtosecond stimulated Raman spectroscopy, which is a tool to look at vibrational data, and I don't have the time to discuss this because the time is running out, but I will just mention this, that it is a tool to extract Raman signals in the excited state. And many of your material samples I know many of you are working on excited states in materials. Many of the materials are amenable to Raman detection. And this is an ideal tool to look at structure on the excited state of a material because you get vibrational data. So the way this principally works is you excite a sample which is flowing in your cuvette because these are femtosecond pulses. You need to make sure the photo damage doesn't happen. So these are flowing, and then you bring a Raman pump picosecond pulse and a femtosecond probe, and you probe this signal, and what you get is a Raman signal at the end, which is a spectra at the end, which is arising because you get an excited state, and then the excited state on the excited state after the first pulse, which is actinic pump, you sort of bring both the Raman pump and probe together, which creates a vibrational coherence in the excited state within vibrational manifolds of the excited state. And that vibrational coherence decays away with another interaction with the pump, which is a picosecond pump. There are two interactions with the pump, and you can generate a Raman photon. The way this works is when you have the pump on or pump off, you get a ground state Raman feature. You put the pump on, you change the ground state Raman feature because you have excited 20% of the molecules to the excited state. So you get a shoulder of the excited state. You subtract the excited and the ground state to get uh, sort of a differential Raman spectra between the excited and the ground state, which only talks about how much excitation is there because there is a bleach and then there is a new signal that you see on the shoulder. You fill the bleach, you remove the bleach to get a pure excited state, and then you do a baseline correction, and you get purely the excited state Raman spectrum. We can discuss this again in the question answer session, how this is done, but just believe me that this can be done with an excitation pulse that clearly allows us to detect excited state spectra. So now when you do this experiment, you get this beautiful data where you get a series of Raman spectra all the way from 200 femtoseconds, 500 femtoseconds, 1 picosecond, 2 picosecond, 3 picosecond, and so on and so forth. You get individual Raman spectra as the state is progressing from a radical cation to a neutral radical. And what we found out was in the Raman spectra, unlike the absorption, transient absorption, which was 60 picosecond in time scale, there was a dramatic change in modes in 30 picosecond, much faster than what was we were seeing in the transient absorption. Also, what is exciting about this spectra is the the Raman spectra compose the entire Raman spectra is composed of the molecule Raman spectra and the cage Raman spectra. So you can see that the cage Raman spectra is very clearly there are lots of modes between 800 and 1800 wave numbers. There are lots of modes. The molecule Raman spectra also has lots of modes, but if you look at the complex, that means when the molecule is inside the cage, it is dominated. You can see here, and I can show you this. It's dominated by the cage Raman modes. Only this mode is a molecule mode. This mode is another molecule mode, and that small one is a molecule mode. Rest all are cage features. But when you look at the excited state, look at this, the clarity you get. This is all the complex, the molecule, molecule, and the rest is cage. All of them disappear. The cage spectra just disappears. And only what we see is the molecule spectra. Okay? So it's very clear that the excited state is full of molecules. And why is that the case? Why do we see only the molecular Raman features in the excited state? Because if you look at it, and if I go back in my, sorry, this is, I need to rub this off. Yeah. So if I go back and look at the molecules, um, Absorption spectra, the radical cations absorption. Look at the radical cations absorption spectra. It has a feature at around 800 nanometers, okay, close to 800 nanometers, and a feature at 470 nanometers. Now, the cage does not absorb at 800 nanometers. The cage absorption, as you know, I showed it. If you go back to the spectra, here, this is the spectra of the cage. The cage absorption dies at 400 nanometers. But the radical cation has absorption at around 700, somewhere here. So it is very clear that Raman spectra that we get here is all from the radical cation, because the Raman was done with an excitation pulse of 800 nanometers. So resonantly enhanced Raman, this is resonance Raman of the radical cation, ensures that I only see radical cation modes and no cage features are observed. The cage should have an anion radical, but we don't see it at all. And that's the power of resonance Raman. Selectively on the excited states, you can get the features that you want to see. The molecule, how the molecule is doing the chemistry. We only focus on the molecule. So this is one of the big advantages, and this is how you can distinguish Raman and IR. Because IR, if you do excited state IR measurement, all the modes in the system will be elaborated. So we did this very nice deconvolution of the Raman spectrum, and it was very clear that the radical cation has a lifetime of 30 picoseconds. And this is a very nice features, as opposed to the neutral radical, which is the features are only seen at the low frequency region and no in the high frequency region. So um, by calculations, we could justify that this particular blue spectra arises from a neutral radical. And the neutral radical has lost its CH bond. The CH3 has become CH2, as you can see it here, that you can see that this is a CH2 moiety rather than a CH3 moiety. See, the CH3 moiety was there in the radical cation state, but this is a CH2 moiety. And now all of this CH2 is in plane with the thiophene. That makes sure that these intense modes are observed in the low frequency region, while the C double bond C stretches are lower in intensity. Calculation gives you that insight into this particular structural change. So we can watch a CH bond activation in real time, and that actually happens in 30 picoseconds and not in 60 picoseconds, as told to us by the stimulated Raman spectra. So this told us that proton coupled electron transfer reactions have a very important aspect of the water structure, because the water structure allows for the first proton to be removed, and then the equilibration happens in 60 picoseconds, and hence the absorption spectra responds in 60 picoseconds, but the Raman spectra responds in 30 picoseconds, because it's only looking at the molecule when it has lost the proton. So this is a beautiful way of using absorption versus Raman and disentangling the actual reaction time scale. So the PCET happens in 30 picoseconds in this case. So when we looked at that and we asked the question, okay, well, this is very nicely done. And I think I'm running out of time, Jayanto. Maybe I take 5 minutes to wrap up. Yeah. So with that conclusion, we could demonstrate that you can do PCET in this metal organic this cages with the CT state and the proton transfer taking place. But can we do it in things which do not have metal in the capsule? So Debajyoti and Shrindita, they demonstrated that in Sir Fraser Stoddard's cavity, which is all organic, you can do exactly the same chemistry and you have no role of the palladium. So if organic chemists or inorganic chemists ask us, look, the palladium is there, why don't you conceive of an idea that the CH bond is activated with the palladium and not through this charge transfer chemistry? We demonstrate here that you don't require palladium for any of this CH bond activation chemistry. You can do it in a all organic cage and you can do it in acetonitrile or water. So this was a demonstration that clearly showed that this is a PCET driven paradigm which is metal free. So I will just stop by showing this one example, and I will summarize because the time is up. So once we demonstrated that we can do this chemistry, and this chemistry is independent of the metal, then we went on and demonstrated the first example of a CC coupling reaction inside the cage by creating two radicals and coupling the two radicals with this particular class of substrate, a phenylacetylene substrate, where we demonstrated that you can create a radical site at the alkynyl CH bond, and you can couple, make a Glaser coupled product of a CC bond. And this was a big deal because till that point, everybody knew that metals are required for this, but you can do this in a cage. And we demonstrated that using transient absorption and EPR, that radicals are indeed formed. We could make a photocatalytic photoredox scheme where these two molecules are inside the cage. You create a radical cation and then a neutral radical in one of the systems and do a CC coupling. And once the CC coupling is done, the electron comes back from the cage and you generate this long rod of a molecule. And since this is such a long molecule, the cage cannot contain it. It has to be eliminated, and the next molecule comes in and gets filled in. So the two ways of doing enzyme like chemistry we have shown, one is if the product is slightly water soluble, you can throw off the product from the cage. There's no trapping. If the product is long inside the cage, it's too large, so sterically it can't be contained, so it can be thrown off. So that allows for this cycle to come, back up. So this can go through its enzymatic cycle because of these reasons of elimination of the product. So we kind of summarized all of this chemistry in this article, and we demonstrate that you can do photoredox chemistry in water with these cages, going through radical cation, neutral radical, and reactions after the neutral radicals form. So I'm not going to take much time, and I just say that we have shown quite a bit of new chemistry in the last 5 to 6 years. You can read some of these published work, but it's actually enabled us to get to CH bond oxidation reactions, radical cation mediated chemistry, as well as CC bond coupling chemistry. So I'm not going to delve too much now into it. So I'm just going to conclude and going to sort of state that um, you can sort of look at this chemistry from a time scale perspective. That's what my takeaway is for all of you today. That this chemistry was planned in hierarchical levels of dynamics. Okay? Dynamics of the system. First is the dynamics of the charge transfer process, which is hundreds of femtosecond to picosecond. Then modulating, the next step would be the proton transfer reaction to water, which can take place anywhere between 10 to hundreds of picosecond. And if you plan this according to these time scales, by hundreds of picosecond, you have a neutral radical in your system. Okay? And you can make use of this neutral radical for any kind of reaction. And the functional chemistry can emerge from that point on to microseconds or seconds time scale. And this is where the real understanding of the next steps for us as a group and everyone would be how to sort of look at fluctuations, equilibrium fluctuations in the system, dynamics in the system after the neutral radical has been created. So this is something that we are working on now in our group extensively. The ideas that we have generated over the last 10 years are translatable to other systems. If you're working with proteins, in fact, Todd Heister's group has shown that you can take the same idea. You can create CT states in proteins with flavoproteins, for example, proteins that have already good chromophores in them, and you can bind substrates and make a CT state within them, and you can do chemistry. So again, a CT mediated chemistry with visible light activation can be done. And these can be translated in principle to things that you think are confinement. For example, in different kinds of supramolecular architectures, as well as in metal organic frameworks and covalent organic frameworks. Okay, you can take the cavities in these frameworks and you can think of CT states with the wall of the framework, and you can photoexcite and do this chemistry. The other way to think about this would be in between nanoparticles. Those are also electric field induced confinements, and you can actually polarize bonds in this high electric field environments. So, according to me as a chemist, the canvas is only limited by your imagination. You can choose any kind of confinement and you can sort of get to this. So, with that, I conclude my talk, and I would like to give my heartfelt thanks to all of you for inviting me, especially to Janto for emailing me and giving this opportunity to share some of the science that we do in the lab. I also want to thank all my graduate students who have crossed the barrier, finished their PhD, and are now, some of them are now independent investigators on their own right, and doing some very great science. So I want to thank everyone with that. I don't know. Maybe it was too fast, Jayanto. I don't know. Was it clear to you or? That's okay. Right. But do tell me if there are questions. But that was some simple questions. You don't have to really. Okay. But let first other people have a chance. Or maybe they're all overwhelmed. Maybe you can start, Jayanto, then. Okay. Yeah, have a discussion. In the ha. Yes. Yes, that's right. Yes, great question. So, Janto, we don't think it that way. See, this particular cage has a slightly different volume, okay, from the cage that Fujita's cage that we use, the metal cage, the palladium cage. Okay, so let me go back to the slide where I showed all the cages together. Here, here, Janto, can you see this slide? So the Stoddard cage is here. You can see on the rightmost side, and the Fujita system is here. Okay. Now these two have different volumes. The Fujita's cage can take 4 molecules of say toluene or 2 molecules of anthracene, but Stoddard system can only take 1 molecule of anthracene. So because of the volume change, the the chemistry has to be slightly different. However, however, the paradigm of the chemistry is the same. It's charge transfer, mediated electron transfer, and then proton transfer, right? The paradigm of the chemistry is the same, but the success rate of the chemistry will be dictated by how this packing is going on of the molecule with the cage. So that will be volume dependent, right? So indeed, the yields in Fujita system, we see for specific class of reaction is slightly compromised as compared to the Stoddard system, which is much more tighter bound. So the molecules don't get a chance to spin and rotate and lose the photons energy. So Stoddard system is much more beneficial in terms of the yields. Yes. Because you can have other orientations, right? And that may not allow the CT chemistry to take place. So you can have losses. Yes. I am not sure about that. I can't give you a very good answer on that because we have not done this for similarly looking cages. But that's a good question, and we can think about that problem. But I would not expect if it is purely PCET driven. Now, Janto, you can have a situation where the metal is involved. Okay, if the metal is involved, then the yields will be different. Yeah. Then you can have electronic effects. Yes, absolutely. You should be able to derive slightly different yields by changing the metal. Yes, right. Absolutely. I mean, we have not done those. We have not done those experiments, but in principle, we are in thinking of replacing palladium with platinum. Okay, and platinum should have a poorer interaction with the CH bond than palladium. So uh, yes, yes. So we want to if but if there is no effect, then it's purely PCET driven, right? There's no role of the metal. Yeah. Okay. No. So we do this spectroscopy called time resolved spectroscopy, right? So I'll just show you this simple idea that so maybe this slide is hidden, or I can derive another slide for explaining the pump probe scheme. Just give me a second. Just give me a second. Um, yes, yes, of course. So I'm opening up a slide where I can explain to you what I did in terms of. Can you see this slide? It's a different presentation, but this is the idea, Janto, that what you can do is you can sort of start a reaction with an excitation pulse, okay, and you can bring a measurement pulse after the excitation pulse has gone through at certain time delays. Okay, this is called pump probe spectroscopy. What we do is we take snapshots of these states as it is evolving in time scales, and these pump and probe pulses have different spectra. So the pump is only exciting a narrow part of your absorption spectra. Say, suppose you have a molecule absorbing at 500 nanometers. I only want to excite the 500 nanometer band. So I will have a narrow pump spectra. Okay, Janto, are you with me? Okay. So, and what we will do is with a probe, which is going to measure the absorption spectra, I will bring a white light. Just like in any absorption spectrometer, I have a lamp. So I will bring a femtosecond lamp, which has color in all wavelengths from 400 to 1600 nanometers. So now this lamp will detect absorption changes. So if I have created an excited state that absorbs at 600 nanometers, there will be photons that will be eaten up here at 600 nanometers. Okay, passing through the sample in the excited state. So those states can be plotted as transient absorption spectra, which allows for absorption transients to be recorded at different time scales after the pump has been put, and you get spectra for excited states, which are different from the ground state. See, the ground state here is an example of a carotenoid system. The ground state here decays away at 650, but you have excited state spectra, which are at 650 or 670. Okay. So you see that all of these are excited state spectra. And what you do is you watch how these things decay away, and you can construct lifetime traces by fitting the decay of these populations. That's like kinetics. You have an exponential decay for an original concentration of the substrate. This is exactly that is an exponential decay of states, and you can get lifetimes after fitting the decay curves. Okay, so it's basically a stopwatch. So you collect after excitation what you probe, and you see absorption spectra, say after 1 picosecond, after 15 picosecond, after 500 picosecond. All of them will give you different excited state absorption spectra, because the molecule is evolving in the excited state, no? So the color is changing as it is evolving, and you can measure this using like a stopwatch idea. So this is basically a pump probe spectra, and you collect these snapshots and you put it up on time, just like this. Just like this, you have a series of these snapshots and you construct these spectra, and these spectra can be plotted either way, like this in time, step by step absorption spectra, or they can be in a contour where they are all added up. All these spectra are now the vertical lines. This is the lambda, this is the spectral line, and that's time profile. In time it is evolving. You see a spectral feature that evolves from 1 to 10 picoseconds to a new spectral features in 10 to 100 picoseconds, and then a final spectral feature at nanoseconds. Do you see the evolution states? So this is how we collect our transient absorption movie. So these are typically in femtoseconds. So that's how we get lifetime information. Right. Yes, that's it. The major question. I think that's the major question. How do we think about the cage, right? So one of the things that I did not show in this talk was this shape of the cage matters. Okay, Janto. So look at this. This is a cage. These are two different cages. Okay, one is a cage that is octahedral shaped, and the other is a nanoball shaped. Okay, see, so the nanoball shaped cage has ligands all across, like a vessel, like a cup. All of it is covered, blocked. But this cage, the full cage, as I've written, it has two walls on the top, like this, if you see my hand, and two in the bottom, like this, tetrahedral symmetry. So there are pores in the top part on this direction, open parts, right? And in the bottom on this direction. Okay. So 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 the cages can have their own symmetry, and symmetry alters reactivity. So we are at the process of understanding what dictates, how the symmetry dictates the productivity. So this is one such very interesting comparison. Kishan showed that you can take the same molecule, put it in this full cage, and get an oxidation product. But if you put it in the half cage, you get a CC cycloadation product. So it is a huge aspect of understanding the symmetry of the cage that dictates the chemical reactivity. So if you go by the reaction, the rules are not yet set by us or anybody at this point. We will have to self-assemble the molecules inside the cage. We will have to look at different classes of cages and see what the reactivity profiles are. Then we can generate enough rules, schematic rules, for you to tell, look, Joyanto, if you want to do that reaction, pick that cage, right? So we have not evolved into that state as yet. We are still trying to understand self-assembly in the cages. So self-assembly of the molecules inside the cages is guided by molecule-molecule interaction, also the molecule-cage interaction. So if I have a very well-known, thought-out computational method, I think we can predict the self-assembly, but we still can't predict the reaction. So my guess would be, let's take different topology of the cages, do optimization of the molecules computationally, and then maybe predict from there what could be the energetics of chemistry and try it out in experiments. So that would be my best guess of how to pick cages. Right, right, great, great. I don't think. I think just maybe um, if you can switch on your videos, that would be helpful. I could see everyone and thank everyone once again. So because it's a online talk, it's very difficult to you know get connected. Yeah, thank you, Pratap. Thank you, Gaurav, Roshali. Yeah,
Thank you, Prof, for giving us the lecture.
yeah,
Very
yeah, yeah.
insightful lecture.
Yeah, well, thank you all for being here and lunchtime. I'm sure you guys are busy with all the research that you're doing, the wonderful research you're doing. I just want to tell you that NTU is one of my favorite places. I was offered a position there in 2010 in the chemistry department, and you can, they're good friends, Hao Siang Tan and Ji Henglo. Ji Henglo is a physical chemist in um, in um, in chemistry. And Hausia, they're very good friends of mine. We were supposed to start together with Ji Henglo, but I chose to come back to TIFR. But um, thank you again for coming for the talk. And if you have any questions or if you want to come to TIFR, do send me an email. It will be great. I'll be very happy to see you. And especially if any of the Singapore students are here, please do visit India and Mumbai. Of course, the Indians I see on the video, but please do come and see the academic environment and the facilities in TIFR. So I'll be very happy to host all of you. Sure, sure. Thank you, Janto. Yeah, take care, everyone.
Thank you, Prof. Thank
Thank you.
you.
Thank you.
Thank you, Prof.
Thank you very much.